Hello and welcome back to Calculus 2, section 7.4 on trig integrals, on trig substitution, trig substitution. So last class we did trigonometric integrals, and now we're going to use those trigonometric integrals. The idea here is to change integral that would look something like this. Let's say you have square root of 16 minus x squared dx, right? You look at this integral and there is nothing you can do about it. You can't use u substitution because there is no x in front of the square root for u sub, right, for du. You can't use integration by parts. So there is literally nothing to do here. It's not basic integral, right? So you're staring at this and you say, okay, what can I do? Well, you recognize that this form of the square root of 16 minus x squared is something that you would see within the Pythagorean theorem. So maybe we can change this integral somehow into a trig integral and then go from there. Now, the conversion from these integrals into a trig integral is very straightforward. It does take a little bit of work, but it utilizes Pythagorean theorem, and it's very quick to set up. Now, before we do this problem, let me talk briefly about Pythagorean theorem and the triangle and the setup. So, if you have a regular right triangle with sides A, B, and C, and you have a right angle, right? You know that you are able to write Pythagorean theorem as a squared plus b squared is equal to c squared. So sum of the squares of two legs is equal to the square of hypotenuse. Hypotenuse is the longest side. Now, I'm going to actually write this as c squared equals. So I'm going to erase the formula now, and I'm going to write it as c squared equals a squared plus b squared. That's better, actually, to explain things. Now, what I'm going to do is I'm going to solve this formula now for a squared, which is c squared minus b squared, and I'm going to solve it for b squared, which is c squared minus a squared. So these formulas, remember that lengths are always positive, right? These formulas will give rise to three formulas. One says c is equal to square root of a squared plus b squared. One says a is equal to the square root of c squared minus b squared. And the last one says that the b is equal to square root of c squared minus a squared. So this is set of formulas where you can solve for the length of any of the sides. Now, if you observe the structure of the problem and the structure of the formulas, do you guys see that our problem has a minus in it, and then the two bottom formulas have the minus in it? Do you all see that? So now, you okay, Chewbacca? All right. Chewy. So now, we are going to have a square root of 16 minus x squared. And I'm going to compare that to square root of c squared minus, let's say, a squared. All right, look at this. You clearly see that if you have a minus under the square root, the first location is hypotenuse. If you have a plus under the square root, both entries are legs. That is really helpful because just by knowing that, I can immediately set up my triangle. You pick angle theta right there, and you know that this side is 4 because c squared is equal to 16. It's just one-to-one correspondence. And no matter which one you pick, if you pick the middle formula or the bottom formula, they both have c squared first, and then minus, and then the legs. So I pick 4, for hypotenuse because it must be there. Now this x squared I can put either here or there. It doesn't matter. You pick one of them, right? So let's pick on the bottom, for instance. It doesn't matter, right? And then what happens is, if you solve Pythagorean theorem for this, the unknown side will be actually 16 minus x squared. Your job is to learn how to set up this triangle when you see a problem. The rest is a walk in a park, so to speak. So if you are able to understand this, you already have your stage set for, you can create your trigonometric functions, and then you can use those trig functions as a substitution. So let's take a look at what we have. Once you see a problem, in our case that problem is square root of 16 minus x squared, right, dx. We use the whatever is under square root to create the triangle. Again, the way we create it is you ask yourself, is it plus or a minus? If it's a minus, the first number is hypotenuse. If it's a plus, two numbers underneath are legs. You put the numbers anywhere you want. So now, since the 16 was the first number and it was a minus, then 16 is guaranteed to be hypotenuse squared. So if hypotenuse squared is 16, then hypotenuse must be 4. The minus x squared, so that minus part tells you that the first number is hypotenuse squared, the second number is one of the legs squared. Doesn't matter which one. So you pick x to be on the bottom. When you do Pythagorean theorem for this side to get the missing side, you will always have entire square root in that spot. Now these two can be swapped and no harm done, because we say the right triangle has hypotenuse and two legs. So it doesn't matter which one goes where. Great. Once we are set with the triangle, I'm just going to move this triangle a little bit to the right because it's in a way of, there we go. So now that we have the triangle set up, I have the angle, right? I can write trigonometric functions. Now, the way you pick which trig, we have 6 of them, right? You always write basic trigonometric functions towards the number. You see, one of the 3 sides will always be a number. In our case, we have 4. So I will circle 4 and x, and I will circle 4 and a square root. So these are the pairs that I will be using to create my trig functions. Again, every time you do a problem, you are going to have a number, like number 4, or 5, or 7, on one of these sides. You will circle that one towards the other 2 sides. So you always use the side that has a number to make these trig equations. So the red equation now, well, this is hypotenuse and adjacent. That's a cosine, right? So cosine theta is equal to adjacent over hypotenuse. Do we see that? And now from there, I can solve this for x, which is 4 cosine theta, and immediately differentiate that because, guys, I need to replace dx as well, all right? We are replacing everything under the square root, but I also need to replace dx. So as soon as you find x, you immediately differentiate, so minus 4 sine theta d theta, and now we have substitution for dx. Now, the blue trig equation is going to be sine, because sine is opposite over hypotenuse, and that is going to give me square root of 16 minus x squared divided by 4. From where you can solve it for the square root. Square root of 16 minus x squared is equal to 4 sine x. I hope that you see now that it's easy for us to do the substitution. Our problem is integral 16 minus x squared dx. So all I do is I swap parts. What do? I take this part, which is this, and replace it with what it is in the trig terms. So it becomes 4 sine x. Bueno? Then I take dx, which is given here, and I replace that as well. So now dx is given by negative 4 sine theta d theta. Simplify, kick out negative 16 in front, and have integral of sine x, cosine x. Wait, hold on. Are they both sine x?
Okay, they're only divided by the 4, you change the theta to that.
Oh yeah, there's supposed to be a theta here. Thank you. They're both sines, right? Right? Sine squared theta? So 4 times negative 4 is negative 16, sine times, oh, that's supposed to be theta, yeah. Thank you. So sine theta times sine theta is sine, what am I doing over here? Sine theta d theta, there we go. Oh, nightmare. The rest is previous section. Now you have to solve trig integral. What you see on a screen right now is the method that we are learning today. So this is all you are learning. From this point on, right, from the last expression in black that you see, that is when 7.3 takes over. If you can integrate your trig functions, you're good to go. If you can't, well, you're done, right? What you see on the screen is a trig substitution. You are starting with a problem that does not have trig in it. Now, it has a structure that we can write around a right triangle, and they all fit nicely so that when we write the trig equations, we get the pieces that are getting replaced. Now, one equation will always give you x. So sometimes it's red, sometimes it's blue, whatever. One of the equations will always give you x. You need that equation. There is no single x to replace anywhere in this problem. In some problems, you will have x squared, x cubed, and you will need to plug that in. But this problem doesn't have a single x to be replaced. However, you always need to find single x because its derivative is dx, and you always have a dx that needs to be replaced. Just like you always have a dx to be replaced by du when you are using your u sum. So your job is to figure out the substitution for each individual part of the integral and dx. So that's exactly what happened on the bottom. I found from my red equation, I found the equation for x, and from there I differentiated to get my dx. You know this because it used to be u and then du, so now it's x and dx, same thing. And we use the blue equation to come up with what the square root is equal to. So now square root is replaced with what square root is equal to, which is 4 sine theta. And then dx is replaced with a negative 4 sine theta d theta, which is this part. And then from here, you go and you integrate. So now we are going back to yesterday's lecture. Yesterday's lecture was 7.3, trig integrals. How do we integrate this? Very good. So we go negative 8, integral of 1/2 cos, minus cosine. No, why did I say 1/2? It's just 1. I kicked 1/2 outside. 1 minus cosine 2 theta d theta. See you next week. So now it's negative 8. Integral of 1 is theta. And integral of negative cosine is negative sine. It preserves the sign. So it's sine 2 theta over 2. And then we have plus c. Okay, fine. See, You distribute negative 8. It becomes negative 8 theta plus 4 sine 2 theta plus c. Now, no one cares about your theta variables. That was you. You had to go and figure something out to solve the problem. The answer must be in terms of x, right? And you have your answer in terms of theta. You are not done. Now you have to convert back. Now, how do we go back? You see, if you had memorized the formula, you would memorize this, right? You would use that. That would be placed into here, and with a little bit more work, right, you will obtain this and you will just go from there. So if you're memorizing formula, but see, the problem with memorizing the formulas, you don't have this picture, and I do. This picture is good for setting up trig functions, but it's also equally good enough for setting up inverse trig functions, which is actually what we need now. Now look at this. You go here and you say, oh, I have sine 2 theta. How do I deal with that? Well, that's going to be a trig identity. Look what I get now. Negative 8 theta plus 8 sine theta cosine theta plus c. And look what's beautiful. I already have what cosine theta is equal to and what the sine theta is equal to. I just need to plug that in. Right? Oh, wait. I have to deal with the theta first. That's not an issue. You can just get theta from here. Theta is inverse cosine of x over 4. There we go. That's theta. We're going to use that. So, the a theta, theta is inverse cosine of x over 4. Perfect. That's that part. Plus 8. Now, what's sine theta? Sine theta is the square root over 4. So square root of 16 minus x squared over 4. And what's cosine theta? Cosine theta is x over 4. Plus c. So now, this becomes negative 8 cosine inverse of x over 4. And then plus 1/2 x square root of 16 minus x squared plus c. Problem solved. It's 8 divided by 16, right?
Oh, I see. Never mind.
Right, so it's half. Okay, good. So, yeah, there we go. There you have it. This is the full trig sub problem, and I'm afraid to say this is probably the cheapest one you're going to see. This is the cheapest and the shortest you are going to see. These problems are awesome for like killing time and carpal tunnel and stuff like that. It's really good. I go, Let's review from the start. You have your problem, and then you use the formulas up here. If there is a minus, right? If there is a minus, then your first value is the hypotenuse, and the hypotenuse goes on the longest side, and then you have the other value, right? Either b squared or a squared. You put that anywhere you want. Do you guys see that if you swap x with a square root, all would happen for the problem is sine and cosine would switch? That's the only thing that would happen. That's it. You would still be able to do the whole thing. So it doesn't matter where you pick to put your x. It will matter later, because later you will be either getting the secant tangent pair or cosecant cotangent pair, and you really don't want to work with a cosecant cotangent pair because it has all the minuses around. But for now, it doesn't matter what you pick. Plug all the substitution in. Once all the substitution is in, you work until you get to the end where you have to go back from the trig into the x domain. Now, the way we do that is we replace theta with either as cosine or sine, whatever you want. And then over here, sine theta, well, that's our blue equation. You see the whole thing, sine theta, like a block, is replaced by square root. And then cosine theta is x over 4. And then plus c, you do a little bit more algebra, and you are good to go. Right? The problem is solved. So all of the trig substitution problems are done this way if you want to use the Pythagorean theorem. Without Pythagorean theorem, well, you memorized this when you see the shape of the problem. You memorize that, and then you keep plugging these things in. You get the same. You get at the same place, and then you go from there. Okay, let's take a look. So I'm going to get, I believe the textbook has like 5,000 examples on this for you to practice. So it will not be a shortage. All right. Hi, Miss Sharif.
So quiet.
I know. It's freaking me out. Sharif, if you're listening, come back.
No one said Imagine.
No one said Alk2, exactly. No one said I.
I was thinking about it, but it's like, it's not the same.
No, it's not the same. Okay, one page that I need won't load. And as I said, that it loaded. 44 problems for you to practice. This is what the homework page looks like in a textbook. Integrals. 44. So you have plenty of these to look at. What do we have? 25 minus x squared. We just did 16 minus x. Is this the same problem?
Yeah.
No. This is 1 over, and the other one we did was on top, right? Uh-huh. This is the same problem we did with 100 instead of 16. So take your answer and you fix a little bit of a constants, right? The base for our problem was 4. The base for this problem is 10. The rest of the problem is the same. Aha, x squared divided by the square root of this. You always use the square root part to create your trig substitution, and then you are using whatever else is there, you also have to substitute that. Then you get to a problem that doesn't have a square root. Yeah, not a big deal. Right, you will still work it as if it had the square root, and you would square both sides to get to that form. You have a square root over here, but it's -3. Okay, you just get the square root and then put it on the exponent, -3. So there are a lot of these little subtle things that you have to practice, but the procedure of setting up and working out an example is going to be the same problem to problem. So let's take a look at another example. I want to work one with the plus. Oh, perfect. Problem 20. Problem 20 says integral dx divided by 1 plus x squared raised to 3/2. Okay, when something is raised to 3/2, like x to the 3/2, that is square root of x, everything cubed. This piece of algebra better be cleared, otherwise you are gone in this section. That's that. So 1/2 is a root, and then you had the third in the numerator, that's going to be exponent of 3. All right, so now that we are done with that, we go and we solve the problem. So where do we begin? Well, we draw the triangle first. Put the angle theta there. And then we say, oh, it's a plus. Plus means 2 legs in the triangle. Okay, so this leg is 1, and this leg is x. Or you can swap them, I don't care. And then this one over here must be square root of 1 plus x squared, because Pythagorean Theorem says that sum of the squares of the sides of the legs is going to be the hypotenuse squared. So we are setting up this triangle by realizing that there is a plus, and if there is a plus, then both numbers inside are legs. If it's a minus, the first one is hypotenuse, and the second one is one of the legs. Pick which one. Great. Now I am going to do my circles. Always circle towards a number. So square root is circled with 1. That's one trig function. And then the blue one is x and 1 are circled. All right, so blue equation, that one is easier. Blue equation is clearly a tangent. Tangent theta is x divided by 1. Because tangent is given as opposite over adjacent. So tangent theta is x over 1, from where I get that x is tangent theta, and then the dx immediately. The derivative of tangent is? Very good. So secant squared theta d theta. So that's immediately from the blue equation. I already have some substitutions going. Now the red equation. Red equation is a cosine, right? It's a cosine equation. I have that the cosine of theta is equal to 1 over square root of 1 plus x squared. Now we need to solve for 1 plus x squared square root, because that's the piece that we have to substitute. So now from there I have that the square root of 1 plus x squared, if I flip the left side, I have to flip the other side, so that is 1 over cosine theta. And 1 over cosine theta is secant theta. And this is actually what saves our life, because we have a tangent and the secant for the blue. You can't have a cosine in the next one. That's not trig pairing for calculus. Trig pairing is sine with cosine and tangent with secant. So blue equation already told you this is going to be a tangent secant problem. You can't have a cosine floating about, or sine, or anything else. The problem is strictly for tangent and secant pair. So when I got 1 over cosine, I immediately changed 1 over cosine into a secant, because that's the identity, and now I have that. Now, we are not done with this transformation. So far we know that the square root of 1 plus x squared is equal to secant theta. But guys, I don't need the square root. I need square root cubed. So if I cubed the left side, I have to cube the right side. Why? To match three half exponent. If you look on the left-hand side, I do have now 3/2 exponent, because the square root cubed is 3 over 2. All right, so what was my problem? My problem was the integral of dx of 1 plus x squared to the 3/2, and that's that. Great. Integral. What is the dx? Dx is given as secant squared theta d theta. That's in the numerator. Divided by secant cube theta. This is equal to sine theta d theta, right? Sine theta plus c, right? Done. Because secant and a cube will cancel. You get integral of 1 over secant theta d theta, which is integral of cosine theta d theta, which is simply sine theta plus c. Bueno? We're not done. Why are we not done? Exactly, you have to go back to x. Now you're looking at your problem, and if you were to do this problem by memorizing what's given in a book, all you have to work is this, that x is tangent theta. Do you have a tangent theta in your answer? No. Yet the only thing you have in your head is the formula you memorized, right? So what are you going to do? Well, what you're going to do is you're going to go to the picture, and you're going to figure out what sine is from this picture. And sine is x over the square root. Perfect. That's exactly what I replaced for the sine. It's x divided by the square root plus c. Right? It's opposite over hypotenuse. So you just replace that, and there you go. I'll just say look at I don't know what I wanted to write there. I moved on in my head to the next problem, and I'm now oh, thank you. Look at the picture. Yes, look at the triangle. To get sine theta equals to opposite over hypotenuse. And that's what happened. So all of this is sine, and then c is c. Great. I hope you see that we did the same method. Right? I used the Pythagorean Theorem. I set up the triangle. I set up the number towards both functions, right? Dealt with the blue one first, the red one second, and then calculate all the way to the end. All right, so you should have, I mean, you're sitting there idle, right? You should have a problem to enjoy for some time. So which problem do you want to do? Problems 21 through 40.
35.
21. 21 is the same. 37. You said 35?
Yeah. Scratch that. 37.
He said scratch that. We have to go through problem 35, but not now. So 35 needs to be done. It's a very interesting problem to do. It's different than any others. That was a very good pick. We are definitely going to do that problem. Pick something else. 22? Yeah, why not? 22 looks awesome. It looks terrifying, but because it is. Dt divided by t squared times the square root of 9 minus t squared. You can change all of these t's into x's if you really want to. This would be a good time for you to collaborate with your colleagues, right? And try to come up with the answer for this. Your x's are now t's, so you will find the t equation and then dt and then the square root and then plug everything in. Let's see how far you can get. Okay, let's take a look at this together. We start by getting a triangle first. And in this triangle, I have a minus. So the first number must be hypotenuse, so that's 3. And then I can put t, let's say over here. What did we do last time? It's the same problem as the first one. Oh, on the bottom. Okay, we put t on the bottom. No, put it there. Doesn't matter. Let's put it there, because the first time we did it on the bottom, let's do it here now. And then the square root must be here, because it is c squared minus b squared, right, to get us this. And here's the angle theta. Now I'm going to create two equations, the red one, which will give me t, and the blue one that will give me the square root to replace. So for the red one, I have a sign. Sine theta is opposite over hypotenuse, from where t is equal to 3 sine theta, and then dt is 3 cosine theta d theta. We need this piece, right, because we have to replace dt. We also, for the first time, have t to replace. It's t squared. Now the blue equation is going to be cosine theta, which is the square root of 9 minus t squared over 3. From where we know that the square root of 9 minus t squared is 3 cosine theta. So now I have everything in order. I can do the substitution. So the integral now is equal to the integral. Instead of dt, I have 3 cosine theta d theta divided by t squared. Well, I need to square t, so that's going to be 9 sine squared theta, right? We need to square this t. Maybe I should put parentheses on the other side, like this. So we differentiated before we do the square, and then after that we square because we need t squared for the equation. And then the square, so we are done with the dt. We are done with the t squared. The only thing that is left is to replace the square root, and square root is 3 cosine theta. So square root is 3 cosine theta. Right, we see it right there. And that's it. So now 3 cosine theta and 3 cosine theta will cancel, leaving the integral of d theta divided by 9 sine squared theta. The way this works is 1 over 9 is kicked out in front of the integral, and the integral of sine, 1 over sine squared is cosecant squared theta d theta. Now that's a basic integral. What is the integral of cosecant squared? Very good. So the answer is cotangent, negative 1 over 9 cotangent theta. Now cotangent theta needs to be replaced. Cotangent is adjacent over opposite. So negative 1 over 9 adjacent, which is square root of 9 minus t squared, divided by the opposite, which is t, and then plus c. Problem solved. Yes.
But if we put the t on the bottom and the 9 minus t squared on the left, wouldn't cosecant be the secant squared?
Yes, very good.
And basically that
Of course, the answer will be in terms of tangent. Mm-hmm. Why is that right?
Oh, because it'd be inverse. Oh, that's close.
Yeah. So see, if you swap them here, then this one would be different. But when you write this one there, because they're swapped, they will work out to be this again. Because it's a double swap. Right? Sometimes when in mathematics you're working on a problem, you make a mistake twice. Right? You do two wrong things, and one wrong fixes the other wrong, and then you come out with a right answer with having everything wrong in between. Right? Well, this is not, both of those methods would be right, because you swap it here, that swap is here, but it also swap there, so it's two swaps.
So instead of cosine, it's tangent, it'd be tangent for the other way, and then when you put it in terms of, it'd be the same.
Which is what the learning is. See, the students today don't take time to actually learn that. Vast majority of the students, right? So the best thing to do would be to actually now, when you get home, swap these. Same problem. Don't do the different problem. Swap them here. When you go through the whole thing, you must end up with this answer. But you swap these two things just to make sure that you will, and that's where learning happens. It's very easy to ask me, right? And instant gratification, right? That's your generation. And I say, oh yeah, when you swap, it's going to work out the same. And say, oh yeah, okay, cool. And then exam hits, right? You haven't practiced, you haven't explored, you haven't learned. And that's a problem, right? So anytime when you wonder something, you should try to do it, you should try to learn it. If you run into issues, that's why I'm here, right? But exploration and learning, right? And that's actually what separates the average students from, the guys that sit in the back. Because exploration is what, you go home and you say, what if? Well, you try that. You try it immediately. Especially with your integration by parts. Right? What if I make a different choice? Will the problem work out? And if you pay attention at your lab, have you seen the lab too? Right? I have like 30 pages to hand in, right? And that's only half of the lab for next exam, right? Because you have 2 labs due, technically, for next exam. So the longest lab in the whole course, which is lab 2, is covering only half of chapter 7. And that's just because the first 5 pages of the lab are questions on integration by parts, because it's so damn important, right? For your later development, the entire chapter in differential equations will depend on your ability to do integration by parts, which Laplace transforms. So you got to know that stuff. Anyway, going back to trig sub, let's do one more, and that would be the end of trig sub. Because, again, this is getting boring now. We are recycling the same idea. Make the triangle, make the functions, and then, right? So let's, we said 35. Did we graduate to 35? Yeah, we graduated to 35. So by popular demand. Happy? Here we go. dx divided by square root of 3 minus 2x minus x squared. Like, how does this resemble even closely of what we had? What should we do?
We need to do the square.
Who's sitting? Boss. Right there. Boss. You have to complete the square. As soon as you complete the square under square root, you are going to get 2 squared entities, and then you can go and unleash the method as we use it so far. So, okay, let's get busy. Complete the square. See what happens. You guys are so quiet.
Moment in class when you go oh, yeah, yeah. And you know what you said? So she doesn't have to remember anymore. So what she did is she emailed her to the portal of the college, they put the class together, opened it, whatever it is, check her school account, email, to find her email, and spin the class meeting. So at this moment in time, it's kind of really grim unless we actually do now our own research and trying to find out, hey, remember about what the I see. So if you Google that question, I was not telling you the bodies. But I have it on for 99 class. I have to do for the this thing is plastic. It don't look like a this is such a waste of time to do that. Yeah, but yeah, this is such a waste of time. YouTube. No, yeah. No, I got it. I'm taking this right now.
Like while we're doing
Yeah, like right, yeah.
Right.
Like physically right now.
So,
I have 150 or 149, I say. Yeah. The minimum. You need a minor? Nanotechnology?
They offer it somewhere. It's nuts, right?
That's sick. What do you do? What is nanotechnology? Yeah, I know. Right? Basically, it's like really
It's
small.
like, basically you're trying to condense technology into size like where you're manipulating atoms.
Oh, really?
Yeah.
Hopefully, I'm not trying to blow money out of everything.
it's not expensive now, I can't. You don't get to see it on the start.
You ever took a deep breath?
Cheers.
What do you do?
Just
Show
like
it's like nice. Good done. Yeah.
All right. Seems like you guys are done, so let's take a look at this and then go for a break. Completing the square. So I'm going to arrange this in this order. Then I'm going to factor out negative because we have to have positive 1 in front of x squared. And then I'm going to use the formula for completing the square, which is cut b in half and square it, which in this case gives us 1. And then that's the number that we add and subtract within parentheses. So I have plus 1 minus 1 to complete the square, and I still have minus 3. So now I have the first 3 terms give me completed square, which is x squared. So the square root of the first, sine of the second, square root of the third, everything squared. This is negative 4, but because of the minus, it's going to be plus 4. So the integral now, after completing the square, is going to be dx over square root of 4 minus x plus 1 squared. So we transformed the problem into this. Now clearly this is a little bit spicier than what you're used to, but it's still doable, right? We write our triangle, draw the triangle, and then we have hypotenuse to be 2, right? Because there is a minus. Minus means that the first number is c. And then we have, now we don't have x, we have x plus 1. So this is x plus 1, and this over here must be square root of 4 minus x plus 1 squared. So now we create our red equation and our blue equation. The red equation is the one that will contain x in it. So the red equation is sine, because I have opposite and hypotenuse. So sine theta, don't forget to put, right, you have to define theta. So sine theta is equal to, and we have opposite, which is x plus 1, divided by hypotenuse, which is 2. From there, x plus 1 is 2 sine theta, and your x is 2 sine theta minus 1, from where dx is the derivative, which is 2 cosine theta d theta. And all of this work just to get dx. But yeah, we need dx, because there is dx in the numerator. We have to replace that. Now we do the blue equation, and the blue equation is the cosine equation. So cosine theta is equal to the square root of 4 minus x plus 1 squared divided by 2. And from there, square root, which is the piece we need, is equal to 2 cosine theta. Now, the problem that we are solving is integral dx over square root of 4 minus x plus 1 squared. This is equal to integral. Instead of dx, I have 2 cosine theta d theta. And in the denominator, I just have, instead of the entire square root, 2 cosine theta. Can this be any easier? Everything canceled. Integral of d theta is theta plus c. And all I need to do now is to go and run either inverse sine or inverse cosine. Doesn't matter what you put. So inverse sine, let's say that's going to be theta is inverse sine of what? X plus 1 over 2 plus c, and the problem is done. Please, next time someone tells you, what do you know? I know trig sub. Work it out on a napkin. See what happens, right? Watch them try to figure out what is the correct orientation to turn the napkin. Right? That would be awesome. There you have it. That's the trig sub. It's very structured. As soon as you figure out the triangle, you do your substitution, you integrate, and you're done. All of the integrals obviously will be trigonometric integrals from 7-3 because you end up with trig integrals. And then when you end up with having the integral of d theta like this, that's just you celebrate because there's nothing to do there, right? You're done immediately. So we got lucky with this one. Excellent pick. That's that. Let's take a break.